So as Cameron said, I'm going to talk about taut co-oriented foliations. So in this talk, when I talk about a manifold M, it's going to be compact, it's going to be oriented, it's going to be smooth or smooth with corners. It's either going to be closed, or the boundary is going to be a union of tori, or it's going to be a sutured manifold. And if you're not familiar with sutured manifolds, I'll be giving a quick definition later, so just focus on the first two possibilities. And F is going to be a codimension 1 co-oriented foliation of M. And typically it's going to be taut. So some basic definitions. And actually, I should begin with an apology. In the first paper on Eliashberg-Thurston, we engaged in some overly bad notation abuse, but that's been fixed. So in the archives and in the version that's going to appear, it's been fixed. But a foliation is CR, and in this talk, R is going to be either greater than or equal to 0 or infinity, means that there's a CR foliation atlas for MF. So if I have a codimension 1 foliation, I have a decomposition of my manifold into surfaces so that locally they're just modeled on R2 cross R. And a foliation atlas is just saying, okay, well, you have charts, but you're insisting that the charts preserve this foliation structure. And so if you're C0, for example, your tangent plane field doesn't necessarily even exist. So only slightly abusing, so this language is very well established. Candel and Conlin introduced this notation of C to the RS, and we just slightly abused that language, and we explain in our second paper carefully, I hope, exactly what that abuse is. Basically, we're just dropping off his plus. So a foliation is called C10, just means that the tangent plane field is continuous. C infinity 0 means the tangent plane field is continuous, and also the leaves are smoothly immersed. And typically, we're interested today in taut, and taut means that if I have, for any leaf in my foliation, I can find a transversal to the foliation that is that meets the leaf, and that's equivalent to there being a single transversal that meets every leaf. So Eliashberg and Thurston have this great, wonderful theorem from the 90s that we've heard a lot about this week. And so if we start with a closed oriented 3 manifold and a taut oriented codimension 1 C2 foliation of M, and you have to rule out F equal to S1 cross S2, or the conclusion would be false, then the tangent plane field can be C0 approximated by a pair of particularly nice contact structures. And with this audience, I don't know why I'm protecting anyone from weakly symplectically fillable and universally tight, but it's the usual conclusion. Particularly nice means weakly symplectically fillable and universally tight. So as we've seen a lot this week, contact structures and foliations are very, very closely related. And this has inspired a lot of jumping back and forth, using ideas from each of the two fields to inspire proofs and conclusions. So one such is this theorem due to Kronheimer, Mruvka, Oshvaltz, and Szabo. And it tells us that if we have a C2 taut-oriented foliation, then M is not going to be an L space. And Oshvaltz and Szabo asked the question, well, is a converse true? So, for example, if M is a irreducible rational homology sphere, which is not an L space, is it going to contain a taut co-oriented foliation? So, Kazez and I, and independently Boden, proved that you can weaken the assumption of C2 to the assumption that you have a continuous tangent plane field. And it's the same conclusion. So particularly nice, we're thinking weakly symplectically fillable and universally tight. And so then you can move, you can upgrade Oshvaltz-Szabo to conclude that if M contains a taut-oriented foliation, then M is not an L space. So if M contains a foliation, even just a C0 one, then Caligari has a result which tells us that M contains, that there's an isotopic C infinity 0 foliation isotopic to F. So in particular, continuous tangent plane field. And so the Oshvaltz-Szabo theorem kicks in to show that M is not going to be an L space. So why do we care? So we're improving C2 to continuous tangent plane field. And the main reason, or a main reason to care, is that surprisingly these are open questions. So if I give you a manifold and I know it contains a taut-oriented codimension 1 foliation, I don't know whether there's a C2 one. I don't actually even know if there's a C1 such foliation. So that's the main reason. And because of this, all sorts of constructions which are naturally C10 but not naturally C2 tell us nothing about existence of smooth foliations. So differentiability is delicate, but topology is robust. So foliations described using branch surfaces can easily be chosen to have continuous tangent plane field, but best possible smoothness is often a mystery, at least with current technology. So in the remainder of the talk, I want to revisit a construction of foliations due to Gabai with attention paid to smoothness. And I'm just, without shame, going to just assume the necessary background. But then I'm going to come back and I'm going to talk about a construction due to Delman, in which basically, as long as you're happy with pictures, you need to know very little. Okay, so Gabai introduced this notion of sutured manifold. So a sutured manifold is just a 3-manifold M together with a subset of its boundary. So if my boundary is empty, that subset is going to be empty. But in general, that subset gamma is going to be a disjoint union of annuli and tori. So we've got some collection, possibly empty, of annuli on the boundary, some collection of toral boundary components, again, possibly empty. So one very common example of this is to think about knot exteriors. So we can just think about, take S3, drill out our knot, remove an open neighborhood of the knot, and then let gamma be that boundary of the neighborhood of the knot. Maybe a more interesting class of examples is to think about taking a branch surface in the manifold, taking an I-fibered neighborhood of that branch surface, letting y, m be, let's see, I actually did put it in the right manifold. So be a branch surface in y, and then m is just the complement of that special neighborhood of my branch surface. And again, if you haven't thought about branch surfaces, I'll be talking about a bunch of examples and giving the definition later. R of gamma is just the complement of this gamma. And the sutured manifold is taut, means that the manifold is irreducible and the R gamma is incompressible and it's norm minimizing in H2 M gamma. So we can think about sutured manifolds. If A of gamma is non-empty, then we could sort of think about, in terms of smoothness, we've got corners. We've got pieces corresponding to the annuli, and we've got tangent, well, not defined outside my foliation, but we've got manifolds with corners. And there's a well-known result of Gabai, which tells you that if you start with a taut sutured manifold and you're not a rational homology sphere, then there's a particularly nice hierarchy. So something called well-groomed, and I'm not going to define what is meant by that, but just something that's nice enough for nice things to happen. And if you're in the particular case that you're a knot complement, with gamma just being the boundary of the neighborhood of the knot, then in this hierarchy, so we cut open along a surface S1 that's properly embedded in M, we cut open along a surface that's properly embedded in M1, etc. If we're a knot complement, then Gabai proved that you can choose the SI so that they meet so that each SI meets the boundary only in circles. So that's a very nice property to have. And so these nice sutured manifold hierarchies are great because they give you oriented finite depth branch surfaces built up using these surfaces in the decomposition. And this branch surface in turn gives you a family of taut oriented foliations. So sutured manifold hierarchy, branch surface, family of foliations. And here's sort of a hint as to what's happening. So at step, I don't know if it's I or I plus 1 or I minus 1, but you've got this mi, and you're cutting open along your surface si plus 1. And you've got everything is co-oriented, and you can use the co-orientation to move from a spine to a branch surface. And we have situations where we can think about the surface as just running along the boundary of mi and missing sutures, in which case we have this picture cross I locally, or we could have that the surface came in and crashed through a suture, your gamma, your vertical boundary of your I bundle neighborhood of your branch surface, in which case you're creating a branch surface that looks like this. Okay, so I'm going to now say, well, I've just been using the word branch surface, but this actually, I can use these pictures to define what I mean by branch surface. So a branch surface is just a space that's locally modeled either on R2, or we could have double points. So you could think of taking this picture cross I, or we've got triple points. We can think about pictures that look like this. So a branch surface is just something that's a compact subobject in your manifold that looks like this. And when we care about smoothness, we can always choose to, we can always isotope a branch surface so that it's smoothly embedded. And, you know, this is just, forget everything up here. I just wanted to have a very precise statement. But what is important is these branch surfaces carry lots and lots of foliations. But in particular, there exists two classes of foliation that are particularly nice. One which is called, which in this description is labeled F for finite depth, and the other labeled S for smooth. And each is, so you can always choose, carried by the branch surfaces coming from these nice sutured manifold hierarchies. Taut-oriented foliations, and sorry, my manifold is oriented, and so I'm jumping without explanation between co-oriented and oriented, just mean the same thing, transversely oriented also. So each is fully carried by the branch surface. They're going to meet the gamma, the sutures transversely. And if you look at the induced intersection, you're not going to see a ray annulus. F is finite depth, and S is smooth, except possibly along finitely many toral leaves. And if you're in the particular case that you're a knot complement, then you can choose your foliations so they meet the boundary of the knot just in a fibration by circles. So we would just be meeting in a fibration by longitudes. We would be strongly detecting 0 using the language of Steve Boyer. Okay, so smoothness of S is well understood. Recently, Cantwell and Conlon went and looked at the finite depth foliations. So the foliations F satisfying everything. Oh dear, I don't know what I just did. So we can always choose F to be C1. And if you know some extra information, if you know that the boundary of your manifold is non-empty and every component of all gamma has a non-empty boundary, then the foliation can be chosen to be C infinity, except possibly, again, we have this problem of finitely many toral leaves, where the smoothness may only be C1. And then you can insist on C1 tangent to the identity in a neighborhood. But there's this curious other fact. So there are examples due to Cantwell, Conlon, and also Kobayashi, which show that if one requires that the induced foliation on the boundary torus be a foliation by circles, there are examples where C1 is the best possible. So there's some sort of weird thing. There are topological obstructions to smoothness that don't come from the existence of torus leaves. And here's a little example that shows that. Well, statement. Okay, so differentiability things are very delicate. And just to say one more thing about the sutured manifold hierarchy constructions, because you have a sutured manifold hierarchy, you have a finite depth Brown surface, or you have a finite set of decompositions, you've got induction arguments that you can play. And it's, inductions using the finiteness of the sutured manifold hierarchy that allow both Gabay and Cantwell-Conlin to prove their smoothness results. And we can turn to various other constructions of foliations. And unfortunately, on this screen, I have only the ones that I personally have thought about. And so R tends to be kind of heavy. That's just a reflection of I haven't thought about smoothness of any of the others. But the widest class is, if you think about Lee's laminar Brown surfaces and the foliations that you get from Lee's laminar Brown surfaces, his construction involves a lot of Danjois blow-up. So as described, your foliations are typically not going to be C2. And you're going to have to work pretty hard to get C1. And the various constructions that use Brown surfaces typically involve Danjois blow-up. So they can easily be chosen to be C1, 0. They can actually easily be chosen to be C infinity 0. Or you can just start with C1, 0 and isotope to a C0 close C infinity 0. So Caligari has isotope to C infinity 0. And then Will and I just jazzed that up to a slightly different proof, showing that you can stay C0 close to the foliation you began with. And it might be that they Danjois collapse down and isotope to smoother. It might be that they could, that there are other closely related foliations which are smooth. We just don't know. Okay, so now I want to start moving and thinking about actual examples. So this is titled Construction Hybrids Are Possible, and I'll come back and explain what I mean by that. But here's a warm-up example. So here we've reached the picture stage. So suppose I gave you a composite knot in S3. Then, again, way back when in prehistory time, Monasco, closed surfaces and such things were very well understood. And once laminations were introduced, you could easily construct structures such as I've shown right here. So let me explain what this picture is supposed to be. So we're thinking we have a composite knot. So there's a sphere that slices the knot, intersecting it in 2 points. And on each side, we have a knot, or we could have a link. And what we do is just say, okay, start on your sphere and just give yourself a tube. Start over here, give yourself a tube obtained by running along the knot or the link. And then just have those tubes meet in what from the inside solid torus looks like 2 meridian cusps. So I've got this tube, and then it's flaring out, and then you're just joining the sphere that you've cut along. So we look at this, and we say, oh, okay. It used to be that we were very, very excited by laminations, but now we're really, really excited instead by co-oriented taut foliations. But we can extend this lamination to a taut foliation by just noticing that on each side, what we see is just the knot complement for my K1 and the knot complement for my K2. So we can think about just applying a Gabay hierarchy on the left, applying a Gabay hierarchy construction on the right, and getting foliations, where Gabay tells us that we meet the boundary of the neighborhood of the knot transversely. Instead, we just want to say, okay, well, we just want to have the leaves of the foliation, instead of meeting transversely, we just have them spiral around the neighborhood of the knot. So let's see, we have in this picture 3 complementary regions. We have, once we've removed from this, we have this side, we have this side. We also have the sutured solid torus. And inside this sutured solid torus, well, what do we want to do? We want to think about introducing foliation. And in Thomas's talk, we saw a special case of doing this. But it's the same sort of game. As long as we're not doing a surgery, as long as we're not thinking about realizing slope 1 over 0, we can think, well, we're inserting a disk. We're doing a Dane filling of slope p over q. That disk is going to intersect the sutures of the sutured solid torus some even number of times greater than or equal to 2. And then we just have the standard stacked chair construction, which I guess dates back to Thurston or maybe even before. So one moral of this game is, well, if I start with a lamination and I notice that the complement is an I bundle, then I just add product foliation to get a foliation. But often I don't need things to be that constrained. So if the complement of gamma is a taut sutured manifold together with some non-compact I bundles, often the Gabby foliation can extend to the I bundle. So you have the sutured manifold, just play the Gabby game. Typically, the foliation, well, I shouldn't say typically. I'm not sure if I should say often, but as long as when you go into the cusp, you can find properly embedded in the leaves copies of R, then you can play this game and extend to a foliation. And there's this remark, so if you're looking at the old papers from prehistory or maybe history, pre-Perelman, genuine laminations were preferred over co-oriented taut foliations, because then you could get group negative curvature thanks to results of Kazez-Gabay and various other things. So some of the older papers don't even bother to mention that if you have a lamination, you can extend to a co-orient taut foliation. So sometimes you can, sometimes you can't. Sometimes it's only like a little sentence right at the end. But if you want to use co-oriented taut foliations and you're looking at some of these older papers, it's a good idea to check with the author and see whether they extend to foliations. And just as some other examples, we could think about taking a hyperbolic surface, looking at restricting attention to the situation where the geodesic laminations are co-orientable, and you're suspending by pseudo-Nosov monodromy, which preserves that transverse orientation. Then you've got complementary regions, solid tori, and again, you can play this stacking chairs game. And in some talk, at least, the Gabay-Moshe laminations were mentioned. And I'm actually not sure whether there are co-orientable Gabay-Moshe laminations with taut sutured manifold complements. But if there are, then of course you can play the same, well, besides the pseudo-Nosov ones. But if there are, then you can certainly play this game. Okay, so far we've just talked about bronze surfaces that are finite depth. And I want to highlight the fact that this is actually quite a big constraint. So when one's playing games and looking to realize intervals of slopes, or to use the language that Steve was using yesterday, that detect or strongly detect slopes. Here, when I say realize interval, I mean strongly detect slopes. What you end up with are intervals of slopes around the boundary of the decomposing surface S1. So if you're restricting attention, say, to not complements, then you're going to be getting some interval around the longitude, around slope 0. And this is a real constraint because you don't always realize maximal CTF intervals. Here's an example. So if you look at the 5-2 knot by Delman, if you look at the 5-2 knot, then there is a result of Charles Delman, who is somewhere here, yes, right here, and also Ramin Naimi from the early 90s, which tells you that if you have a non-torus two-bridge knot, then any slope in minus infinity, infinity is realized by a taut-oriented foliation. And you can show that the best you can do if you're using a sutured manifold hierarchy is going to be minus infinity 1 open interval. So I want to focus in now on this construction due to Charles, because it's I think the most powerful example of branch surfaces that are not finite depth. And when you're looking at very, very small knots, taking advantage of non-finite depth foliation seems to be key. So I'm giving a very sloppy statement of Charles's theorem, but you can check his preprint from 1990, I don't know when, and he's right here also to ask. But for most non-torus Montesinos knots, any slope in minus infinity, infinity is realized by a taut-oriented foliation. And so recently, he and I were revisiting his result, in large part because of this theorem of Baker and Moore, which tells us that among the Montesinos knots, we know which are the L-space knots. So if we restrict it, sorry, I should tell you what a Montesinos knot is. So you can describe it as a picture like this. So I've got a decomposition of my knot into tangles, and they're all rational. So here I've got pieces of the knot, pieces of the knot, pieces of the knot. And then here I'm thinking I've got some rational tangle. Let me not even try to do anything clever. So maybe I've got a little piece that looks like this, and similarly long here. Any rational tangle. And so you can, in fact, do better than this big statement up here. And mostly, though, Delman in huge capitals, R with a tiny little r, it's really just going back and looking at what Charles already knew to do. And I'll give you a precise statement in a second. But for even more non-torus Montesinos knots, any slope in minus infinity, infinity is realized by a taut-oriented foliation. And just to have an example to think about, smallest, so something that is not in our list, but also not in this list, the smallest Montesinos knot that we haven't, well, I hope it's like we haven't yet, but we haven't managed to find foliations in yet, is -1/2, 1/5, 1/5. But using sutured manifold hierarchy games, you can get minus infinity up to 2g-1. And Dunfield, Nathan is somewhere here, was kind enough to just quickly yesterday compute some large positive slope Dane fillings and found that they do in fact contain co-oriented taut foliations by his construction. And I realize I've been talking way too quickly, but this is a precise statement, but I don't know whether one should really focus in on it too much because it's changing by the day. So let me just click to the next. And here again, I guess I want to emphasize. So 2 observations about the Delman branch surfaces. I've already said they're not finite depth. And also, if you think about, one game is often to think about putting a Morse function on your manifold and then, expressing your foliation or your branch surface or whatever in Morse normal form. He takes very strong advantage of the fact that the branching locus can have extrema. And that sounds like a very sort of obvious assumption. But if you're coming from the world of surfaces, it's actually fairly unique, interpreted in the right way. So I wanted to give an example of Charles's construction, and I thought I would work with the simplest possible example. And so think about the knot 5-2. So if we think about the knot 5-2, that's a two-bridge knot. So that's one that's amenable to the constructions of Charles and Ramin. And it's also a special alternating knot. And if you think about the use of the word special used by Steve yesterday. And I think we call them checkerboard alternating. So if you think about alternating knots, we have an alternating projection. We can think about the alternating projection. Applying Seifert's algorithm to the alternating projection is going to give the minimal genus Seifert surface. And we have sort of two classes, what Steve was calling generic yesterday, which is you've got separating by the Seifert cycles. And the other is the case that one of the two checkerboards, you don't have separating, so one of the two checkerboards is going to give you your minimal genus Seifert surface. So in this picture, the blue is the minimal genus Seifert surface of 5-2, and the red is the other checkerboard. And I chose my colors after Josh's talk yesterday, but I probably went opposite to his convention. So I look at this, and here I'm going to say, oh, okay, well, what does Charles tell me to do? Charles tells me to just slice that red surface, the non-orientable one, open along a plane that intersects the knot 4 times. So as I have in this picture over here. So I changed things so that the red surface is the one I can more easily focus on. And take a slice. And after you've taken the slice, miraculously, on the top, you have what you get if you think about taking that top piece of surface, just that rectangular strip, and then just connecting it by disk. So on the top, it looks like you're just trying to do a Murasugi sum. But on the bottom, something completely non-Murasugi sum is happening. So you move from this object, piece of your knot lying below, to something that looks like this, where you have to have a little piece of surface at the top looking like this. You can do whatever you want here. So when you isotope, when you simplify your knot K, you end up on the top, you have the complement of this Hopf band. On the bottom, you have the complement of this Hopf band. And we're a little bit like in that warm-up example. We now have 2 sutured manifold complements. Well, actually, we have 3 at the end of his game. 3 sutured manifold complements. We have this complement. We can apply Gabai hierarchy in general, but this is pretty simple. And we have this also. I mean, in general, we would apply a Gabai hierarchy, but here it's just a product already. And then the game is going to also have this third complementary region, which is going to be a sutured solid torus with some even number of meridian cusps. Yes. So I'm going to come back and. It's going to be built out of the red surface, the plane, and the green surface. Maybe I'll go ahead and then we'll come back to this picture. And since I'm not as clever as you at using different slides at the same time, we'll have to jump back and forth. So let me go to this picture maybe. So what we're going to want to do is form a branch surface where we have, away from the sphere we cut along, we're just going to have tubes. And we're going to have pieces of, ideally, a minimal genus Seifert surface for the object we get above, minimal genus Seifert surface for the object we get below. So above, you can think of, you've got some tube. These orientations are kind of mysterious at the moment, but here my tube is oriented in the positive sense. Here in the negative sense, my surface is oriented in the plus sense. So if you think about how that complex, how that complex transforms to a branch surface using the orientation, the spiraling from the red on this side is going to end up looking like this, and the spiraling on this side is going to end up looking like that. And similarly, if we go over to here, we have a plus orientation. We've got minus, so we're going to end up with this is plus, this is minus. We're going to have spiraling like this here and spiraling like this on the other side. Ignore the diamonds for the moment. So above, it's going to be easy to see what we have. Away from the sphere, we're just going to have pieces of the original knot and pieces maybe of the original surface, maybe not. But now let's go back. We need to understand what's happening here. Okay, so key in Charles's construction is what's happening in a neighborhood of the knot. And so we've got an assortment of things that can happen. And here are two possible things. So, there's not going to be so many. But, if I look at type 1, of course, I'm going to have all the, I could take type 1 and turn it upside down. I've got various symmetries. Okay, so type 1 is, you should think about, when we go back here, that sphere, that cutting open sphere, that thing that looks kind of brown, it's supposed to be Tuscan red. It appears in this picture as the stuff that is Tuscan red, but also this stuff that's pencil. So locally around one of the crossings, you can think about, you see something that looks like this. So maybe let me just slowly go through what looks like this means. And I can, although this is going to be part of a non-finite depth branch surface, locally, of course, I can describe it in a finite depth sort of way. So I can think about, I have this tube, and then I have a little rectangle strip that I just have wrap around my knot in the front. And when it meets, it begins, you can think about proceeding in two steps. Where it meets first, you're just having it intersect transversely, but then we're playing our branch surface game. So we use the transverse orientation to just pinch to a branch surface. So for example, here, depending on what the orientations happen to be, and they can be, whatever. But let's say I think about, in this one, if this is a plus, then that tells me that this piece of the tube must be also oriented a plus so that it pinches in this direction. And I want something that's co-oriented. If you move up behind, so then this is going to be a minus. And so let's see, so we had the tube, we had this rectangular strip, and then we take another rectangular strip, which is this Tuscan red piece that comes from behind. So in terms of the picture that we see, the red is that piece of the surface, the Seifert surface for the not the Seifert surface, the surface, piece of red surface that's above the cutting open sphere. The pencil and this Tuscan red are part of the sphere itself, which is why you lose finite depth. And then this is supposed to be green, even though it's blue and got fixed. It corresponds to that piece of green surface that we were describing before. Okay, so here, if you notice, if you think about the complementary region that contains the knot, we just have a smooth cylinder. So we just have a smooth cylinder piece with the knot running through. And so no meridians. The diamonds are a slightly modified version of notation due to Ying-Ching Wu. And here the idea is red is what I see above, and blue or green is what I see below. And a diamond means that you've got, this cusp type behavior. So I've got a red diamond if the cusp is opening upwards. I've got a blue diamond if the cusp is opening downwards. So I can capture this picture using this notation right here. So I'm thinking about in the sphere, I see the intersection of the tube with the sphere. I see that I'm going to have two cusps, one opening down and one opening up. And I'm going to have spiraling around in this way. We're interested in chasing sutures. So I can look at this picture and I can say, well, what are the sutures? What's the branching locus of my branch surface? And so I can see, okay, I start here, I head into my knot, and then I've got this thing is spiraling up like this. So if I follow the suture, I'm going to have this. I'm going to wrap around, and well, if I'm not being completely stupid standing up at the front here, I'm going to continue up here. So I'm going to have a suture that runs along the sphere and then just starts following the knot, reflecting the spiraling we have of that R around the tube. And I think that's all I wanted to say about this picture. Are there any questions about what this picture is describing? Okay.
Where did the two surfaces come from in the original diagram?
In the original diagram, the top surface is what we originally saw, the red. The bottom is the green from this thing that's currently a mystery, but I will get to soon. But I need to show another picture, and I'll do that in a second. But yes, so in general, the game is typically on one side you sort of begin knowing what you expect to see as the surface, and you make some choice to make everything work out on top, and then on the bottom you have to clean everything up. But of course, you know, you can switch roles of top and bottom. Okay. So let me put a pause on your question and I'll come back to it. A type 2 crossing is a crossing in which you can introduce a meridional cusp. So if you think back to our warm-up example, where we had sort of the part of the surface and then tubes coming in, and we introduced a cusp when they met at the sphere. So we think about the tube comes along here, it branches out and just becomes part of the sphere, and similarly from the bottom. And again, red you should think of as that's part of the surface that's above. Green is part of the surface that's below. And now we can think about, again, and we've got all sorts of choices. We're wanting co-oriented, so depending on what this local orientation is and this local orientation is, the direction of cusping is going to be determined, and similarly down below. And we can notice that if my tube is oriented positively above, it's going to be oriented negatively below. So as we pass the cusp, we're automatically changing the transverse orientation on the piece of tube. And depending on what orientations we see of our pieces of surfaces, that's going to constrain how we spiral. And again, a diamond indicating that here there's a meridional cusp, so pencil color to indicate it's inside the solid torus complementary region. And again, spiraling determined. And here it's a little easier to see what's happening with the sutures. I have a suture in my sphere that runs up along this red arc, runs up behind, and then continues up here. And then behind I've got a cusp coming from the branching that we see behind, just again running along the surface sphere, below the sphere, and then continuing down along the knot. So this is supposed to get to Yair's question, so you'll have to bother me if I horribly fail, which I probably will. So now let's think about what we have. So we have this red surface above, it's intersecting in an arc. We've got transverse orientations which force the directions of spiraling at the end of the arc. We have, here we have what's happening in a neighborhood of the knot looks like what was happening in our type 1 picture. So we've got no cusp along the torus, but we do have a cusp that is opening down because it's green along the red arc. And so that's happening around this cusp is like our type 1 picture. What's happening around, what's happening around this boundary, this intersection of the tube with my sphere is type 1, same picture right here. So remember, if we want to understand what the cusp locus does, these are opening down. So sorry, I need to think about, these are opening up. So I'm going to have a cusp locus, and then remember we just went up the knot. Cusp locus, we went up the knot. So if we look at the picture that we have, what we need for Charles's construction to work is some sort of reasonable configuration. This is certainly not the only one, but if you understand this one, then you end up pretty much understanding all the possibilities. But so let's think really, really carefully about what this cross-section looks like. So this cross-section, I've got type 1 behavior here, type 1 behavior here, type 2 behavior here, type 2 behavior here. So I've got this picture. So I know that I've got two meridional cusps. I've got a meridial cusp here, and I have a meridial cusp here. The red is just telling me I have the surfaces coming up. So we see red, we see red. But then we've gone instead, remember in the original surface, the blue surface would have, the red surface would have extended down exactly in that slope. The red surface would have extended down exactly in this slope. Instead, we have, because of the choice of what we wanted the picture above to look like, we now have, what we need is that we have a surface coming from below that intersects in slopes, two arcs of slope 1/2. So before we address what the impact of that is on the surface below, let's just follow the sutures so we can see what the resulting branch surface has as branching locus. So topologically, I just see the sphere, I see these tubes, I see the surface coming from above and from below. And in terms of the sutures, I chased one before, so from above we have this suture coming down here, crossing all over here, going along, if I'm going to, let's see, I want to have, in the end of the day, I need to have the right slope, which was supposed to be slope 0. So have I drawn the wrong picture here? I'm not sure. Okay, so we had the suture was here, here. Okay. I've got slope 1. Oh, that's too bad. Okay. It's a problem of going out to dinner with Cameron and Steve. So sorry, I've got the wrong choice here. This would be the choice in which I introduce another half twist, which would make things non-orientable. But if I change this by a tiny little bit, which I will not try to do up here, but I'd be happy to talk about later, or Charles would, I'm sure, be happy to talk about also, you can arrange that the suture just would connect. Let's see if this is what I want to do. It would just connect this, and we would have the complementary piece that we had right here. So we have the picture we saw, and we've added a band. Below, we have to instead think about, now if we think about chasing the suture, and again, I'm going to have the wrong choice, but if I chase the suture up to here, I would then be following, I've got a cusp running along here, so I'd have cusp running along here, and then running along here. So in this, I've exactly switched where I add the extra half twist, but I would be insisting that the surface that I started with was this, now instead of the surface starting at slope 1, 0, it's starting at slope 1/2. So you can think about, you can instead think about that you've modified the knot below. You've modified the knot below, you've cut open, and you've spliced in this new slope, in this case 0/1, but in general something more, and you've got a continuous surface down like this. So if we go back to this picture right here, we added, if I'd drawn the right picture, we would have added a half twist here. We would have this thing of slope 1/2. We can think about, we've got this picture, we've got a sphere. The original knot is just hanging down as it did before. We have to complete the surface, which now is green. To make my life simple, instead of seeing my surface looking weird up here, I can untwist it to look again like it's slope 1 over 0. But then, of course, I've added some twists into how my knot continues on. So by changing the picture so that it still looks like slope 1 over 0, we have to add these 2 extra twists to our surface. And, in this example, we can untwist, and we can complete our surface to this green surface that we have right here. And there are other variants of this observation of Charles. So he also observed that if you're doing you could think about this as a step in a sutured manifold decomposition, or something. Right, you could think about this as a step in a sutured manifold decomposition, except instead of the usual crossing picture, you're thinking of your surface as spiraling around the neighborhood of the knot, and you're thinking about introducing a meridian on the boundary. And it's not surprising to notice that depending upon whether your crossing is a right crossing type or a left crossing type, so I've adopted right veering and left veering, you're going to have different orientation possibilities. There is a constraint. So in this one, if you look at what happens, it has to be that as you pass in the positive direction along K, the orientation passes of the tube around the knot passes from negative to positive. And you see sort of the sign constraint. If instead you're doing a left veering type crossing, as you pass in the positive direction along K, the orientation moves from positive to negative. So you've got that appearing this way. And here's just another obvious sort of behavior you could see around the boundary, which is introducing it's not introducing any sort of meridian cusp in the complementary region, but it just gives you a little bit more freedom. So the example that I just described takes advantage of a non-orientable surface and a Conway sphere sigma. Conway sphere is not essential. And in general, you can think about just starting with your knot K and finding some other surface. Maybe it's a Conway sphere. Maybe it's a sphere that intersects the knot in 8 places. Or maybe it's a surface that actually has genus and crosses the knot. The game is always going to be you would like to find a taut sutured manifold above and below so that you can fill in and get transversely oriented foliation. So
can you choose the orientation on the below piece and the above piece arbitrarily? Do you have to choose them such that they coincide as there are left piece of the bigger thing? Or
no. The beginning red surface was basically just used as a crutch. So in general, you could imagine that you wouldn't start with such a crutch. You would just have the knot lying in your manifold in general, and you would have something that was slicing through. And then what is constrained is how. So I sort of think of this as a Delman sum, where I have a piece above, a piece below. If I do a Muritsugi sum, the piece above and the piece below get changed in very natural ways, and you get the K1 and K2. Delman, something more subtle is happening. But you're modifying, if you add, you have these strands, you have the branch locus, they give you a new link. You're looking for a minimal genus Seifert surface for the link above, a minimal genus Seifert surface for the link below, and then you are hoping that you can find such that meet. You are constrained. You have to, if I've got this picture that I had before, in general, you're going to have pictures like this. And you would need to be able to find, a minimal genus Seifert surface or some nice branch surface type object that met in this slope. So you're constrained in how the surface has to start and end, but you get to choose what's happening up here. If it's possible to be optimistic and say you have a choice. In general, it's difficult to make a general statement, or at least with what we understand now. Yes. And let's see, are there examples? I mean, I guess in all the examples that we can handle, we've got some sort of crutch surface that's helping us begin. And the stuff on the top looks very close to the surface we began with, and the stuff on the bottom is a little bit weird. And maybe a good warm-up example, which I just figured I would not have any time at all to go through, is to think about the -1/4, 1/3, 1/3 pretzel and try and play this game. So if you this is an example where you need to use both a combination, well, I don't know if you have to, but an easy thing that works is to use one of those cutting open spheres, and then also to use a product disk decomposition of this Delman sort to get the orientations on the tubes and to get the right number of meridians. But there's all sorts of variants. It's just difficult to give some sort of reasonable general statement. Okay, and I decided that no talk at this conference was complete without a Libman result. So here we have a conjecture by Libman and Moore that an L-space knot has no essential Conway sphere. And so it's a very natural question to ask. Are they coherentable Taut foliations realizing minus infinity infinity if K contains an essential Conway sphere? And initially this feels really, really close to something that Delman's construction should work for. But we don't know how to use this. And thanks.